Yeah, thank you very much for the invitation. I think this is my first QCD Meets Gravity, and I'm very excited to be talking about something that is related to what seems to be a major theme of this workshop. So this is mainly based on a paper from July, and it is in the context of so-called celestial amplitudes, which I've been thinking about for a while. But the connection to the double copy has really only kicked off once I started talking to Eduardo Casali, who has been a fantastic collaborator in this project. So to put this into context, let me start with a bit of motivation. So usually when we discuss scattering amplitudes, we use plane waves as asymptotic states. But there exists another very convenient basis of wave functions, which goes under the name of conformal primary wave functions, which make some conformal properties of scattering amplitudes manifest. And this arises quite naturally because the four-dimensional Lorentz group SL2Z acts on the celestial sphere at null infinity as the global conformal group. And as a consequence, we can recast four-dimensional scattering amplitudes as two-dimensional correlation functions on a celestial sphere. Now, by studying these two-dimensional correlators, the hope is that we get powerful constraints on the quantum gravity S matrix when recasting the spaces, and potentially get new insights into hidden structures or symmetries of amplitudes. Now, having such a conformal structure begs a natural question, which is, could it be that the four-dimensional space-time physics is holographically encoded in some boundary theory? So this question actually, in some sense, goes back almost half a century, where the symmetries of asymptotically flat space-time were discussed. And it was found that the Poincaré group actually gets infinitely enhanced to the so-called Bondi, Van der Burg, Metzner-Sachs, or BMS group. And then in more recent years, it was found that this can be further enhanced to a Virasoro or DFS2 asymptotic symmetry group. And so now the question is there potentially a dual celestial CFT living at the boundary of asymptotically flat space, which encodes what's happening in the bulk? And over the past couple of years, there has been a lot of research in trying to unravel some of the properties of this putative celestial CFT. And wouldn't it be wonderful if such a celestial CFT exists that would give us sort of a non-perturbative definition of quantum gravity in asymptotically flat space? The purpose of this talk is to introduce this new conformal basis of wave functions and how it gives rise to celestial amplitudes. And then I will go to the main part of this talk, which is to show how the famous property of scattering amplitudes, known as the double copy, arises for celestial amplitudes. Now, we expect the double copy to be a fundamental property of amplitudes, so we expect it to be present in all kinds of amplitudes. But in the case of celestial amplitudes, a little puzzle arises that will have to be resolved. So let me start with discussing this map from the four-dimensional scattering matrix to a two-dimensional correlation function. So here, the scattering matrix with external particle labels given by the energy and a null vector, which is parameterized in terms of points on the celestial sphere where particles enter and exit, and the helicity label L. This gets mapped to a correlation functions of operators which are inserted at these points Z and Z bar on the celestial sphere, and which carry the quantum numbers under the global conformal group. Those are the scaling dimension delta and the two-dimensional spin J. Now, the way to go from this basis of momentum eigenstates given by these plane waves to a new basis of conformal wave functions is achieved by a so-called Mellin transform. This is an integral transform from 0 to infinity over all the energies with this particular factor of omega to the power delta minus 1. And in this way, we can go from momentum eigenstates to boost eigenstates, which I denote for the scalar case by phi delta, and which is just given by 1 over the product of this null vector times the spacetime vector x to some power delta, and it comes with a normalization factor. Now, to go from the scalar wave functions to spin 1 and spin 2 wave functions, all I have to do is attach the appropriate polarization vectors and tensors, and I will call these wave functions V. And notice that the two-dimensional spin label J is identified with the four-dimensional helicity label. Now, via this Mellin transform, we can go from a delta function normalizable basis of finite energy plane wave functions to a new basis of wave functions where the normalizability condition enforces that the conformal dimension delta lies on the so-called principal continuous series of the Lorentz group. So that means that the real part of delta is 1 and the imaginary part is a real number. And so we can go now from massless states given by the labels on the left to operators on the celestial sphere. And in particular, the energy is now traded for the conformal dimension. So this was for wave functions. Now we can go to these so-called celestial amplitudes, which arise when we do a Mellin transform on each of the external particles. So for the usual scattering amplitudes in the plane wave basis, we have in particular this four-dimensional energy momentum conserving delta function, which makes translation symmetry manifest. But once we once we do a Mellin transform over all the external particles, translation symmetry becomes obscured. But on the other hand, conformal symmetry becomes manifest. To be very explicit, under an SL to Z Lorentz transformation, which means a Möbius transformation on the angle variables Z and Z bar, these so-called celestial amplitudes do indeed transform as one expects for a two-dimensional conformal correlation function. And so this provides a new way of looking at quantum field theory scattering amplitudes. Now, as an example, let's just take a 4-point amplitude. Celestial amplitudes are given by a general structure, which is given by this universal factor, where the Zij's and the Z bar J's are just the differences of points on the celestial sphere. And the exponents here are just the conformal weights, which are related to the conformal dimension delta and to the spin in this way. And then there's this conformal factor in front, F, which is just a function of the conformal cross ratios, which is given by this expression in gray. And now as an example, the MHV for gluon and for graviton amplitude given by this expression for the stripped amplitudes gives rise to a conformal factor for Young-Mills and gravity, where in black, I denote the term that we would expect from a usual two-dimensional 4-point correlator. But then for the celestial amplitudes, we also have these rather unfamiliar terms in color. So in particular, a remnant of the 4-dimensional energy momentum conserving delta function is this delta function in blue, which restricts the conformal cross ratio Z to be real. And then in red here, we have remaining Mellin integrals, which in the case of Young-Mills theory is just marginally convergent. And so we can express this as a delta function that restricts the sum over all the conformal dimensions. But for the gravitational amplitude, on the other hand, this is in general divergent. So celestial amplitudes have some peculiar properties as compared to the usual two-dimensional CFD correlators. And what I want to do next is discuss this remarkable property of amplitudes known as the double copy in the context of celestial amplitudes. So there are many incarnations of the double copy, and you know this much more than I do. What I will need for the purpose of this talk is just a statement how Young-Mills theory squares into gravity. So in particular, we can obtain gravitational amplitudes from Young-Mills theory amplitudes by replacing the color factors shown here in blue, which satisfy a Lie algebra Jacobi identity, by another set of kinematic numerators, which are shown in red, which satisfy this color kinematics relation. And this way we can obtain gravitational amplitude by a squaring of these Young-Mills numerators. Now, what I want to emphasize here on this slide is that we have in the case of the gravitational and the Young-Mills amplitude, this 4-dimensional energy momentum conserving delta function. And in order to show that the gravitational amplitude is indeed obtained via this squaring procedure, one makes heavy use of this fact. On the other hand, this raises a puzzle because in the conformal basis, as I mentioned before, translation symmetry gets obscured. And so you might wonder how or if does the double copy even arise for celestial amplitudes. Now, if we think that the double copy is an underlying fundamental feature of amplitudes, then surely a change of basis should not change that. And it should survive in some form or the other. But the question is how? So it turns out that the most natural generalization when we compute amplitudes using the usual Feynman rules in a setting where we don't have manifest momentum conservation is to keep this momentum conserving delta function as an integral expression. And so for the rest of my talk, I will be looking at squaring relations of integrands where we keep these spacetime integrals explicit. And this procedure was already introduced by Eduardo and his collaborators in the context of extending the double copy to curved backgrounds, in particular, in this case, to plane wave backgrounds. And so provides another incentive for studying the double copy for celestial amplitudes, because we do need a generalization, as in the case for the curved space double copy, but without having the complications of curved space. So let me start by reviewing the usual momentum space double copy by keeping this energy momentum conserving delta function as an explicit spacetime integral. So we have the contribution to the amplitudes coming from the 3-point vertices, and here I'm allowing myself to be using complexified momenta. So we have this expression for the 3-point amplitudes, and when plugging in the spin 1 and spin 2 plane wave functions, we get expression that we can massage. And normally we use momentum conservation to show that the Young-Mills numerator, shown here in red, squares into the gravitational one, but we cannot do this here because we have kept the explicit spacetime integrals. But the equivalent statement here is that we integrate by parts. And so we make explicit use of the fact that partial derivatives acting on wave function produce factors of the momenta, and these momenta are spacetime independent. And so the double copy statement here is, once we strip off the product of all the scalar wave functions, we have a squaring of the integrand. Now, let's try to just do this for the celestial 3-point amplitudes. So here, instead of the plane waves, we now have the Mellin-transformed plane waves, and attached to it the polarization vectors and tensors, which I take to be a square of the polarization vectors here. To mimic the way that the partial derivatives act on the plane wave functions, now in the case of these conformal wave functions, I introduce generalized celestial momenta denoted by capital K, which are now spacetime dependent momenta. And this is something that also arises in a curved space double copy. So now the Mellin transform of the amplitudes that I showed on the previous slide is now given by similar expressions, but the plane waves are replaced now by the scalar wave functions, these conformal wave functions, and the usual momenta denoted by little k are now replaced by this capital K celestial momenta. And so now, as before, what we try to do is we try to integrate by parts the gravity integrand to see if there's a double copy structure. And what we find is there is not. So the Young-Mills integrand does not double copy into the gravity integrand. And the reason is that via integration by parts, we get extra terms, which are not present in the Young-Mills amplitude. And these extra terms arise because these celestial momenta are now spacetime dependent. And so you get these extra factors of squares of the momenta that come with powers of the conformal dimension delta. So how do we fix this? So our proposal for a celestial double copy is the following. You should, instead of using the celestial momenta, you should promote them to differential operators, which we denote by curly k, which are defined to act on this conformal wave functions phi, as given in this box here. So acting on the wave function, they reproduce the celestial momenta capital K, but they also keep track of the particle label. And therefore, they are not equivalent to the usual partial derivatives. They emit a nice presentation in terms of these null vectors that point to the celestial sphere, and an exponential operator which shifts the conformal dimension of the ith particle delta. And this representation is nothing but the action of the translation generator of the Poincaré algebra acting on the coordinate of the ith particle. So that's a very natural thing that appears in this context. So now let's try if we can fix the double copy for these 3-point amplitudes. So instead of the celestial momenta, we should now replace them in every place by these differential operators curly k, which now means that instead of having the numerators in the integrand, we have operator valued numerators. And those act on the wave functions. And the question is whether the Young-Mills numerator squared promoted to an operator has the same action as the gravity numerator. Now, in the case of the gravity numerator, we do the same as before. We integrate by parts to massage this expression, which gives us these extra terms that are not present in the usual momentum space double copy. But now, because we have promoted also the Young-Mills numerator to an operator, the action of the wave function produces also extra terms. And these come from the action of a product of these celestial operators with the same particle label. And as you can see, the extra terms that are produced exactly match. And we get the result that the operator valued gravitational numerator acting on the wave function is precisely given by the operator valued Young-Mills numerator squared acting on the wave function. So we get a celestial double copy from 3 gluon amplitude to a 3 graviton amplitude. Okay, so much for 3 points. And now let's see how or if this works for 4 points. So there the story is a bit, sorry?
5 minutes.
Thank you.
Left. Yeah.
The story is a bit more complicated because now we have these 3 channels, which have a dependence on 2 spacetime points x and y, and we have these contact terms. In order to proceed, we open up the contact terms by using these properties of the propagator, which then gives us contributions to each of the 3 channels. And long story short, we can describe a 4-point Young-Mills amplitude by a spacetime integral over the points x and y. We have the scalar propagator g, and then we have a contribution from each of those channels. The capital phi's are just the product of the scalar wave functions, the plane waves namely. In blue are the color factors, and then in red we have these kinematic numerators in terms of the momenta and the polarization vectors. And the momentum space double copy just says that these color factors, when replaced by another set of numerators in each channel, gives rise to a gravitational amplitude. And so after stripping off these plane waves, we get an integrand squaring in each channel. Now let's see if this works for 4 points in the celestial amplitude, where after a Mellin transform, we obtain the same structure. But now, instead of the plane waves, we have these conformal wave functions. The color factors are the same, of course. And then instead of the numerators with the little k's, we now get these space-time dependent numerators with the celestial momenta capital K. And now the naive story would be that we just replace the color factors by another set of these space-time dependent numerators. But unsurprisingly, this doesn't give rise to the gravitational 4-point amplitude. So what we should do instead is follow the prescription that I just gave. So everywhere where there are celestial momenta, we should replace them by these operators. Then once we have done that, this means that all the numerators are now replaced by operator valued numerators in each channel. And after that, we replaced all the color factors by a set of these operator valued numerators. And then we get an expression. And the question now is, does this expression correspond to the celestial for graviton amplitude? And in order to show this, we will use some properties of the Mellin transform. So this celestial for graviton amplitude should also be given by the Mellin transform of the momentum space 4-point graviton amplitude, which we know can be written in this form where we have this numerator squaring in each channel. And this expression depends on the energy of each particle in a polynomial fashion. And so when we Mellin integrate over all the external particle energies, there will be essentially 2 cases. One is when the energy arises in a linear fashion, and the other is when it arises in a quadratic fashion. And this then gives rise to these extra terms. And these extra terms here mirror the action of these celestial differential operators on the wave functions that I have shown you before. And so it means that this expression that we get from our celestial double copy procedure is indeed the celestial for graviton amplitude. And so we have shown that the celestial for graviton amplitude can be obtained from the celestial for gluon amplitude via a celestial double copy. So I think I'm almost out of time. So let me just finish with a few points of discussion. So I've shown you how to obtain the celestial version of the double copy statement. But this also gives rise to an interesting presentations for amplitudes, because we can start from scalar amplitude and go to Young-Mills and to gravity by having this promotion to operators. So for the 3-point amplitudes, we can start with this scalar amplitude and obtain a Young-Mills amplitude by acting with this operator valued numerator. And similarly for gravity when we do the squaring. This also goes up to 4 points, where now in each of those channels, ST and U, we have an operator valued numerator that gets squared. And we can go from a 4-point scalar amplitude to Young-Mills and to gravity by the action of these operators. The celestial double copy also generalizes to higher points. This has been explicitly shown in a beautiful recent paper by Eduardo and Atul Sharma, where they also showed the celestial version of the scattering equations and they obtained color kinematical dual numerators from the Amplitudes twistor string. And this leads me to another question, which is, what's the best way to describe the celestial double copy? And the point here is that our prescription is reminiscent of recent results on ambitwister strings in ADS. And so perhaps the best way to discuss the celestial double copy and maybe even celestial amplitudes is via the ambitwister string. And then another point is that can we extend this double copy procedure to other theories and beyond tree level? And here for celestial loop amplitudes, there are only a handful of results so far. One that we have found for the 4-gluon amplitude in planar n equals 4 super young Mills involves similarly to this operator curly k that I introduced. It similarly involves this dimension shifting operator, and we can obtain an all loop celestial amplitude via the action of this operator on a tree level celestial amplitude. And an interesting question here would be to generalize the celestial double copy to loop level. Okay, I think I'm out of time, so thank you very much.
Thank you for a very nice talk. Yeah, so I think we have plenty of time for questions. So go ahead if there's somebody who has questions. While we're waiting for people to raise their hand, maybe I can ask a question. So I guess one question I have is when you go to this celestial amplitudes, you do this Fourier transform, and I guess my question is what happens with the effect?
Sorry, I did not hear that. What happens?
Sorry, yeah, maybe I'm not asking very clearly. So gravity is not conformal, and you're going to a basis of conformal states, eigenstates. And so what is there a problem there?
Yeah, so in the beginning, I showed you this for the 4-part amplitudes in particular, this remaining integrals, which for gravity is not convergent.
They're not convergent.
For young Mills, you can write this as a Dirac delta function in the sum over these lambda j's. But for the gravitational one, it doesn't. One thing to point out is that there are graviton states which have real conformal dimension. So if you insert those in one of these amplitudes, then formally you can shift these lambdas so that you can incorporate this real dimension graviton. But for a general amplitude where all of the gravitons lie in the principal continuous series, this is divergent. And in the case of 4-point and presumably higher, you can go to string theory in order to soften this behavior. And there has also been very nice work on string amplitudes and celestial string amplitudes.
A related question, would it be interesting to look at conformal gravity in 4D? With that, I suppose that would be better behaved in some sense. Well, it has other problems probably, but...
Yeah, but I guess it would be interesting, at least to make sense of this, yeah, these features here.
All right, okay, now I see a couple of hands. So let's go with Svi first.
Just a simple question. Have you thought about the KLT form, what that would look like?
I don't have anything to say at this point about it, no, but yeah, it's an interesting question. There's so many interesting questions, and yeah, the question is which one to look at first. So I don't have any results on that yet. So.
And then I think David was next.
Yeah, thank you for the nice talk. This question's maybe a little bit tangential, but if you have enhanced symmetries in the 4D amplitudes, I mean, I'm thinking of things like dual conformal invariance, for example. Do you understand how that would be reflected in the 2D correlators?
Yeah, so I think this is presumably at work in being able to write the all loop celestial amplitude in this nice way. So we have also found the celestial version of the BDS formula here. So somehow dual conformal symmetry is probably at work here. But yeah, we haven't explicitly worked that out. But yeah, for this case of n equals 4, planar n equals 4 super young Mills, the celestial amplitude is very simple. And you can write a celestial amplitude for at each loop level. And the exponentiated version also takes this very nice factorized form. Yeah, so that's all that I can say in relation to your question.
All right, Lance has a question.
Hey, thanks for the nice talk, Andrea. Just a general question about what do we expect these celestial conformal field theories to obey in general? I mean, normal, well, I should say old-fashioned unitary 2D CFTs had unitarity, positivity, crossing symmetry, factorization. How many of those properties survive here?
So there's crossing symmetry. So I should say that many of the, so what we have is four-dimensional unitarity, right? And however, that manifests itself in the 2D CFT, but it doesn't mean that you have 2D unitarity as you're used to from, let's say, ADS CFT.
Because you don't have real conformal dimensions anyway, right? You have
right,
a bunch
exactly.
Of
so that's one thing.
And they're not constrained by much of anything, I think. You just integrate over all of them with some delta function constraint on the,
There's one thing if you have.
And what about factorization? What about factorization as two points approach each other on the 2D surface?
Yeah. So there is an OPE
factorization?
statement that you can obtain a statement about OPEs, which comes from the collinear limit of the usual for the amplitudes. So people have worked out how they look like, and you can obtain them either from the collinear limit of amplitudes or by looking at constraints from symmetries. So in particular here, I'm talking about asymptotic symmetries, which show up in this putative celestial CFT as operators with real dimension. So I already mentioned this before. So for example, a stress tensor has a real dimension in this CFT. And so it does not lie on the principal continuous series. You can obtain this real dimension or even general complex dimension or operators via certain contour deformation of integral along the principal series wave functions. And those can be shown to give rise to the space-time asymptotic symmetries, which is like Poincaré, and then its enhancement to BMS and its enhancement to Virasoro or DFS2. And then furthermore, there is a statement, the celestial statement of energetically soft theorems. So the factorization that happens there, so you might be puzzled, you integrate over all the energies, how do energetically soft theorems survive? But they do, and what we proposed was that instead you should look at the conformally soft limit, which means that the conformal dimension takes certain values, and these values are in particular real integer or half integer values. And then you can obtain the analog of, say, Weinberg's soft graviton theorem. But
is that something that would work at the loop level too? The soft...
Yeah, that's a good question. Right now, there's only a handful of loop amplitudes that have been computed. So I think this planar equals 4 super Young-Mills one is maybe one of the simpler ones. I know there's some upcoming work by other groups, but there is not much work on that yet because that's one of the more difficult things to tackle. Yeah, but that would certainly be a very interesting question to look at. Mm-hmm.
Thanks.